The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I will respond as soon as I can. All right, so today we're going to go on and cover section 9.3, which is simplifying and combining radical expressions. First of all, I want to introduce a couple of rules that we already know in terms of exponents, but I want to look at them in terms of radicals as well. So the first rule would be this. If we have a product, let's say A times B to the n power, so we have a product raised to a power, the rule says that we attach the outside power to each factor on the inside. So the quantity AB to the n equals A to the n times B to the n. We could expand this further and we could say, what if the exponent instead of n was 1 over n? Then we would get A to the 1 over n times B to the 1 over n. No big difference there. But what if we took that expression or that equation, whatever, and we rewrote it in radical form? Then what we would have is the nth root of the quantity AB equals the nth root of A times the nth root of B. What this is saying is that if we are taking a root of a product, we can write that as the product of the root of each factor. For instance, let's say I have the square root of 9 times 4. That's equal to the square root of 9 times the square root of 4. The square root of 9 is 3, the square root of 4 is 2, and we get 6. We could also take 9 times 4 and say that's 36, and the square root of 36 is 6. So we get the same result either way in this case. But the point is, we could take a product, that the radicand being a product, and separate it into the product of different radicals. Okay, so that's the first rule. The second rule is similar, but it has to do with a quotient raised to a power. When we have a quotient raised to a power, we attach the outside power to both the numerator and the denominator of the quotient. So likewise, if we had the quotient A divided by B raised to the 1 over n power, this would be A to the 1 over n power divided by B to the 1 over n power. If we translate this statement into radical notation, we would have the nth root of the quotient A divided by B equals the nth root of A divided by the nth root of B. And this is our second rule that we're going to be using today. So again, these rules go back to exponential situations, but we're now doing it in radical notation. All right. So one of the topics of today is called simplifying a radical. And we need to kind of define what we need by simplifying a radical, because when sometimes simplifying a radical, the final form looks more complicated than the original form. So you're like, well, where's the simplifying coming in? Think of it this way. Simplifying a radical means getting everything that we can from out from underneath the radical, okay? So for instance, if we have the square root of 4, we can simplify that to just 2, and we've completely gotten rid of the radical. But what if we have the square root of 8? Well, the square root of 8 in and of itself is irrational. It doesn't come out nice or nicely. But we could take that and rewrite it as the square root of 4 times 2. 4 times 2 is 8. Then using these rules, we could rewrite that as the square root of 4 times the square root of 2. Then we could come back and say, well, the square root of 4 is 2. The square root of 2 is still irrational, but we could go this far. So the square root of 8 is equal to 2 square roots of 2. Now, again, 2 square roots of 2 looks more complicated than the square root of 8. The two quantities are equal, but by definition, 2 square roots of 2 is simplified because we've reduced the quantity that was inside the radical. We've got a smaller number inside of there, okay? Now, when dealing with square roots, the idea or the trick is to find factors inside that are perfect squares so that we can unsquare them and kick them outside. So for instance, let's take the following problem. The square root of 28. I want to break down the radicand inside so that I have perfect square factors and leftovers. Now, 28 is 4 times 7. 4 is a perfect square. 7 doesn't break down any further, so I could rewrite the square root of 28 as the square root of the quantity 4 times 7. Then I could rewrite that as the square root of 4 times the square root of 7. Then I could take the square root of 4 and get 2. The square root of 7 can't simplify further, so my final answer is 2 square roots of 7. So the square root of 28 simplified becomes 2 square roots of 7. All right, let's take a look at another example. 9 times the square root of 54. So the 9 is already outside, so we don't need to do anything to it that's special other than whatever we take out will multiply by that eventually. Well, let's see, 54 is 9 times 6. 9 is a perfect square. 6 breaks down into 2 times 3, but neither of those are squares. So I would rewrite this as 9 times the quantity, not the square root of 9 times 6, which then becomes 9 times the square root of 9 times the square root of 6. But the square root of 9 is 3. So now I have 9 times 3 times the square root of 6, or 27 square roots of 6. So 9 square roots of 54 simplified becomes 27 square roots of 6. Let's take a look at another problem. This is the cube root of 40. Well, we're no longer taking a square root, we're taking a cube root. So now we want factors inside that are perfect cubes. So let's see, 40 could be written as 8 times 5. 8 is a perfect cube, 2 cubed. So the cube root of 40 equals the cube root of 8 times 5 equals the cube root of 8 times the cube root of 5. But the cube root of 8 is 2, so we get 2 cube roots of 5, and I can't simplify the cube root of 5. I could get a decimal approximation, but I couldn't get an exact answer other than what is there. All right, another example, the fourth root of 32. So now we're not looking for perfect squares or perfect cubes. We're looking for perfect, I don't know, fourples or whatever, but something raised to the 4th power. Okay, so let's see, 32 is 2 times 16, 2 times 4 times 4, 2 times 2, hang on here. Let's see, it would be 2 times 2 times 2 times 2 times 2. Oh, so that would be 2 to the 4th power times 2, or 16 times 2. My point is 16 is something to the 4th power. And if you already know that, then you wouldn't need to go through this process. But I could write that as the 4th root of 16 times 2, which would be the 4th root of 16 times the 4th root of 2. But the 4th root of 16 simplifies down to 2, so I get 2 times the 4th root of 2. I want to go back and do this problem again, and let's do this. So we determined, or I determined, that 32 was 2 times 2 times 2 times 2 times 2, right? Or 2 to the 5th power. Well, since I'm taking a fourth root, I could think of it as 2 to the fourth power times 2, okay? Well, the fourth root of 2 to the fourth times 2 would be the fourth root of 2 to the fourth times the fourth root of 2. Why would I want to write it like this instead of like that? They're equivalent, but I want you to notice the fourth root of 2 to the fourth power is just 2. How do I know that? Well, for instance, the fourth root of 2 to the fourth power, writing that in exponential form would be 2 to the 4/4, or 2 to the 1 power, or 2. So in other words, the exponent and the index, when they match, they reduce down to an exponent of 1. Okay? In general, I like to say the nth root of a to the n equals a if a is greater than or equal to 0. Okay, the nth root of a to the n. So what does that mean? Well, for instance, what's the cube root of 7 cubed? That would be 7. What's the fourth root of 8 to the fourth? That would be 8. What's the 15th root of 200 to the 15th power? That would be 200. Okay. All right, back to some more examples. This says, simplify each radical expression. All variables represent positive real numbers. So that means we don't have to concern ourselves with absolute value bars because they're telling us that all the variables are positive. All right. So we've got the square root of 50x squared. Since I'm taking a square root, I want to break the radicand down into squares and leftovers. Okay. 50 is 25 times 2. 25 is a square, 2 would be the leftovers, and then x squared is also a square. Okay. So then I could rewrite this as the square root of 25 times the square root of 2 times the square root of x squared. But the square root of 25 is 5. The square root of x squared is x. So putting all of the non-radical stuff in front, I get 5x square roots of 2 as my final answer. All right, now, again, I want to go back and do this problem a second way, just because it's a little bit less writing. Rather than breaking it down and writing this step separately, I could just go through and do this and say, okay, the square root of 25 is 5 outside. The square root of 2 isn't going anywhere. The square root of x squared is x outside. So I get 5x square roots of 2. It's the same process. It's just saving writing this step out separately. Either way is fine. All right. New problem. The square root of 75 b to the 8th power c. Okay. 75 is 25 times 3. So I could write this as 25 times 3. Again, 25 is a perfect square. And then let's see, b squared times b squared times b squared times b squared times c. You might be thinking this is ridiculous. It is. I want to do it this way to show you that there's a better, faster way, but I want to start with this. So here I would have the square root of 25 is 5. The 3 is going to stay inside. The square root of b squared is a b outside. The square root of b squared is a b outside. The square root of b squared is a b outside. One more. The square root of b squared is a b outside. And I have 3c left inside. So I've got 5b to the 4th square roots of 3c. Now, the square root of b squared is b, right? The square root of b to the 4th is b squared. The square root of, I'm not sure what that is. The square root of b to the 6th is b cubed. The square root of b to the 8th is b to the 4th. Because in each case, we've got a 2 that's implied as the index. 2 divided by 2 is a 1, 4 divided by 2 is a 2, 6 divided by 3 is a 2 is a 3, 8 divided by 2 is a 4. So what that's telling me is that not only could I simplify b squared, but b to the 4th, b to the 6th, b to the 8th. So basically, if the exponent is a 2, or I should say is the index, or a multiple of the index, I could just deal with it as it is without having to break it down further. So let's go back and look at that again, how I would do this problem a quicker way. Okay, the square root of 75 b to the 8th c is 25 times 3 times b to the 8th times c. The square root of 25 is 5. That's stuck inside. The square root of b to the 8th is b to the 4th. That's stuck inside. And I get 5 b to the 4th times the square root of 3c. Okay, let's look at this a slightly, well, let's do one more of these and then we'll look at it a little bit differently. So let's say I've got the 5th root of 64 x to the 10th y to the 5th. Okay, 64 is 8 times 8, which is 2 times 2 times 2 times 2 times 2 times 2, or 2 to the 6th power. I'm going to rewrite it as 2 to the 5th power times 2 to the 1 power. Why do I want to do that? Because my index is a 5. So the 5th root of 2 to the 5th, the index and the exponent are going to reduce down to a 1, and I'm going to take a 2 and put it outside. Now, x to the 10th, 10 is a multiple of the index, y to the 5th, 5 is a multiple of the index. So what happens? The 5th root of 2 to the 5th is 2 outside. This 2 is stuck inside. The 5th root of 10, excuse me, the 5th root of x to the 10th would be x squared. 10 divided by 5 is 2. The 5th root of y to the 5th would be y. And what's left inside is the 5th root of 2. So I've got 2x squared y times the 5th root of 2 as my final answer. Okay, now, what about, let's see here, let's do this problem. Same direction, simplify each radical expression. All variables represent positive real numbers. The square root of 147a to the 5th power. Okay, well, let's see, 147. What goes into that? 2 doesn't go in. 3 goes in if you add up all the digits. 1 plus 4 is 5. 5 plus 7 is 12. If 3 goes into the sum of the digits, 3 goes into the original number. Well, let's see how many times. 147 divided by 3 is that's a 49. Okay, so that's 3 times 7 squared. Okay, so here's what I'm going to do. I'm going to write this as 7 squared times 3. I could have written it as 3 times 7 squared. A to the 5th. Now 5 isn't a multiple of the index, but I could rewrite it as a to the 4th times a. Why do I pull off a to the 4th? Because 4 is a multiple of the index. Okay, so now the square root of 7 squared is 7 outside. The 3 is still inside. The square root of a to the 4th is a squared outside, and the a is still inside. So now I have what? The square root of 3a. So 7a squared times the square root of 3a. So we've got the takeout and the leftovers, so to speak. All right, let's take a look at this problem. The cube root of 280 a to the 5th, b to the 6th. So I'm looking for cubes and leftovers. off the top of my head, I can't think of a cube that's a factor of 280. So I'm going to break it down using prime factoring. Let's see, 10 times 28, 2 times 5 times 4 times 7, 2 times 5 times 2 times 2 times 7, 2 cubed times 5 times 7. Okay, so 280 breaks down to 2 cubed times 5 times 7. Okay, and I want cubes, or multiples of cubes, so 2 cubed times 5 times 7. A to the 5th power, I'm going to pull that apart as a cubed times a squared. B to the 6th power, 6 is a multiple of 3, so I'll just leave that as b to the 6th power. So now I've got cubes, multiples of cubes, are the exponent, multiples of the index, and leftovers, okay? So the cube root of 2 cubed is 2 outside the radical. The 5 is going to stay inside. The 7 is going to stay inside. The cube root of a cubed is a outside of the radical. The cube root of a squared, since the exponent is smaller than the index, it's not going anywhere. And the cube root of b to the 6th is b squared. Now I'm going to take the leftovers that are inside and multiply them back together, 35a squared. I guess we don't need this. Come on. This doesn't need to be quite so long there. All right. So there you go. We've simplified the radical. We've kicked out all the cubes. The leftovers are still inside. Okay. So we've looked at products inside of a radical. Let's look at quotients inside of a radical. So it's, again, it says simplify each radical expression. All variables represent positive real numbers. The square root of the quantity 3 divided by 4. So we could rewrite that as the square root of 3 over the square root of 4. Well, the square root of 4 is 2. And I can't do anything with the square root of 3 in the numerator, but I've simplified it as much as possible. Okay, here's another problem. The 5th root of 2 divided by 243. Well, let's see. 243, I believe that 3 goes in. 2 plus 4 is 6 plus 3 is 9. 3 goes into the sum of the digits. So 3 goes into the whole thing 81 times. 243 divided by 3 is 81. 81 is 9 times 9. 9 is 3 times 3. And 9 is 3 times 3. Oh, so I've got 3 to the 5th power. So this could be written as the the 5th root of 2 over the 5th root of 3 to the 5th power, which gives us the 5th root of 2 in the numerator. But the 5th root of 3 to the 5th power is going to be just 3. Okay, let's see here. The square root of 128 divided by the square root of 2. So now, well, let's go back. Before these last couple examples, we had a fraction inside of a radical, and we split the numerator and the denominator up. Now we've got 2 radicals making up a fraction. We can go the other direction since the index, or the indices, I'm not sure the plural of indexes, are the same. We could rewrite that as the square root of 128 over 2. But then we could take the radicand inside and say, well, 128 divided by 2 is 64, and the square root of 64 is 8. Okay. Let's take a look at another example. The square root of 75y to the 5th divided by the square root of 3y. That would become the square root of 75y to the 5th over 3y, which would become the square root of 25y to the 4th. 25 over 3, 75 over 3 reduces to 25. Y to the 5th over y reduces to y to the 4th. And now the square root of 25 is 5. The square root of y to the fourth is y squared. So our final simplification is 5y squared. Okay. Let's see here. How about this one? We've got the cube root of 243 x to the 8th over the cube root of 9x. So that becomes the cube root of the quotient 243 x to the 8th over 9x, which becomes the cube root of, let's see, 243 divided by 9. 243 divided by 9 is 27. And then x to the 8th divided by x to the 1 power would be x to the 7th power. Well, 27 is 3 cubed, and x to the 7th, I'm going to write it as x to the 6th times x to the 1 power. Why did I peel off an x to the 6th? Because the 6 is a multiple of the index 3. So now the cube root of 3 cubed is 3 outside. The cube root of x to the 6th would be x squared outside, and the cube root of x left inside. There you have it. Okay, now we're going to simplify expressions by combining like radicals. And let's look at that. Let's go back to the idea of like terms. If I have 2x plus 3x, that is 5x. 2 of something plus 3 of the same thing is 5 of the same thing. What if I had 2 square roots of 7 plus 3 square roots of 7? Well, that would be 5 square roots of 7. So we say these are like radicals and that the radical part of each expression is the same. Okay, now let's look at some examples. Let's say I've got 11 square roots of 3 plus 2 square roots of 3. Well, that would equal 13 square roots of 3. Let's say I've got 30 cube roots of 6 minus 10 cube roots of 6. That would be 20 cube roots of 6. What about this situation though? 9 plus the square root of 45 plus the square root of 20 plus 16. It doesn't appear that we have any like radicals. Well, before we make a judgment on that, we need to make sure that each term is simplified. Each radical term is simplified. So let's see. 45 would be 9 times 5, right? 9 being a square, 5 being the leftovers. 20 would be 4 times 5, 4 being the square and 5 being the leftovers. So doing this, I could now rewrite this as 9 plus 3 square roots of 5 plus 2 square roots of 5 plus 16. So these two radicals at first did not appear to be alike. But once we simplified both of them, the radicand left inside, they were the same, so we can now combine them. So we're going to take the whole numbers, 9 plus 16 is 25, plus the like radicals, 5 square roots of 5, and there's our final answer. Okay, let's take a look at another example. Let's see here, we've got the square root of 20 plus the square root of 125 minus the square root of 80. It doesn't appear that we have any like radicals, but let's simplify each radical and see what shows up. Okay, so 20 could be written as 4 times 5. 125 could be written as 25 times 5. And 80 could be written as 16 times 5. Now, What I did was I pulled out the largest square factor in each one of them and set that separately. But, you know, maybe you look at 80 and you don't immediately see that, oh, it's 16 times 5. So how would you get there? Well, you could say 80 is 8 times 10, which is 2 times 2 times 2 times 2 times 5, which is 2 to the 4th times 5. Oh, 2 to the 4th, that has an exponent that's a multiple of the index. Okay, so in other words, instead of writing it like this, I could have written it, let's see here, like this, because this and this are the same, right? Either case, simplifying, I'm going to get 2 square roots of 5 plus 5 square roots of 5 minus, this is going to be what? 4 square roots of 5? Or here you'd have what? 2 to the 2nd square roots of 5. Okay, from here you'd get directly to the 4. Here you'd get 2 squared. And then you'd come back and write it like this. My point is, either way, either taking it the square root of 16 or the square root of 2 to the 4th. If you can see the 16 at the beginning, you'd use it. It'd be easier. If you can't, breaking it down, you get the same result. 2 of something plus 5 of something is 7 of something. 7 of something minus 4 of something is 3 of something. The of something being the square root of 5. So our final simplification is 3 square roots of 5. So in this case, all 3 terms ended up being like radicals. Now, that isn't always the case. Sometimes you get you might have 3 expressions and 2 of them you combine and 1 of them you can't. Let me give you an example here. The square root of 80m minus the square root of 128m plus the square root of 288m. So again, I'm taking square roots, so I want perfect squares. We just did 80, so that's going to be 16 times 5 times m minus, let's see, 128 is 2 times 64, 2 times 8 times 8. So what? Oh, 2 times 64. So 64, said one thing and wrote another. So 64 times 2 times m. In other words, 64 is the biggest perfect square inside of 128. And then let's see, 288 is 2 times 144. 144 is 12 squared. So here we've got 144 times 2 times m. Okay, so I've broken it down into perfect squares and leftover factors. Let's see, the square root of 16 is 4. Everything else stays inside. The square root of 64 is 8. Everything else stays inside. The square root of 144 is 12. Everything else stays inside. These two are alike, but the first term is not. So I get 4 square roots of 5m minus 8 of something plus 12 of something would be plus 4 of something, the something being the square root of 2m. So just my point is, don't just assume that every term is going to simplify down to where they'll all combine. Okay, they may not. All right, that's all I have for you today. So again, section 9.3 for tonight. I'll be back at 1:15 today with an office hour. Should you have any questions? Otherwise, I will see you tomorrow, and I'll go ahead and stop the recording now.